bodies. A comet is ice and rock, and it's usually greater than 1,000 meters. We call it a comet if it's greater than 1,000 meters and it's ice and rock. An asteroid is mostly rock. Some ice, but not necessarily. And it can go all the way down to 100 meters. But once it gets 100 meters in size, it's not called an asteroid. It's called a what? Do you know?
Meteoroid.
Meteoroid. A meteoroid is less than 100 meters in size. So if it's bigger than 100 meters, it's an asteroid or a comet. A comet's ice, and an asteroid is mostly rock. A meteoroid is smaller than that.
What's the asteroid? How long is it? How big is it? Okay, you don't.
An asteroid's from 100 and up.
So if it's smaller than 100, it's a meteoroid. If it's 100 and up,
It's an asteroid, and if it's mostly ice and bigger than 1,000, it's a comet.
Crazy.
And then it's a meteor if it hits the atmosphere, and it's a meteorite if it hits the ground.
so comet is bigger than 1,000.
Comet's greater than 1,000 meters. An asteroid can be greater than 1,000 meters too. An asteroid's 100 meters or greater. Does that make sense?
Yes.
There's a lot of words to make sense of here.
And then meteor does not touch ground.
Meteor is anything, it could touch ground. A meteor is anything that's burning up in the atmosphere. If it hits the ground, it's a meteorite. If it hits the ground, it was a meteor, then became a meteorite when it hit. Does this make sense?
Wait, so what about a meteoroid?
A meteoroid is something floating in space smaller than 100 meters.
Okay. And if it comes into our atmosphere, it becomes a meteor.
That's right.
And then
If it hits the ground, it becomes a meteorite.
Okay.
So
Wait,
that
so-
can become that, can become that.
But if a comet hits Earth, that's not a meteorite.
It would technically be at that point. Yeah.
Okay.
If a comet hit the Earth, it would be a meteorite. We don't usually call it that, because if a comet hits the Earth, it's a major catastrophe. Like a mass extinction. Could be here or there. Okay, so
That video we watched of where the Earth
yeah.
ruined, is that like a comet size, or was that larger than a comet?
That was like a small planet size. I mean, well, it was a lot bigger. It was the size of Japan, they said. So it was about I guess Japan's about 1,000 kilometers, something like that. So that's 1,000 times as big as this. So that's big. Question?
Can I think, I know this is all public, can I think about this after lunch? Okay,
Yes.
after lunch, thank you.
Okay, so I didn't talk about meteor showers. So we need to know about meteor showers. A meteor shower is when the Earth passes through the orbit of a comet. So, you know, when a comet comes close to the sun, it gets gas and dust knocked off of it, right?
Mm-hmm.
And especially the dust, those particles will keep orbiting with the comet. And eventually the comet comes completely apart and all you're left with is dust. And the dust spreads throughout the orbit of the comet. The dust doesn't stay in one place, it'll stretch out and go all the way around. And you end up with just this ring where a comet used to be of dust. And if the Earth passes through that ring of dust, you get a meteor shower. And because the Earth is in an orbit that's consistent, you get it every year. Every year the Earth passes through the dust at about the same day. And so you get a meteor shower that day, each year. It's like clockwork. So here are all the meteor showers that happen at different times of the year. And here is the comet the meteor showers are associated with.
Gotcha.
So coming up here, October 9th, we are having a meteor shower.
Oh my gosh.
The Draconian meteor shower is late evening. Go out October 9th at night. Look to the northwest. That's the point of origin, the northwest. You should see 6 shooting stars per hour. Look at that. You missed this one. It's in August. 50 shooting stars per hour.
It's gonna be 75.
Oh my.
I was coming back.
75, December 13th.
Oh, it's gonna be all night.
All night,
That's
baby.
so
Did
cool.
we see the one in July? It might have been August.
Nah.
I seen a shooting star going across like the. I think it was in July.
Well, you can see them on any night. It doesn't have to be, but you get a shower, which is a lot of them on these nights. You get one every hour or so on any night.
I saw one. I was like, oh, that's like the first time.
Oh my gosh. So late evening. So is that like about?
Well, this is the best viewing, but it actually goes all day, all night, all day and night. You can't see them in the day.
Right.
But it'll go all night, and it'll even go a day before and after, because it takes a while for the Earth to get through all that dust.
Is it also ice in that, like rainbow?
Yeah, little particles of ice and dust. That's right. Yep. Mm-hmm.
So you could go out like at like 10 o'clock at night. And
Yeah, you'll see. This is the best viewing, the best time to go.
Like what is late evening though?
Like 7,
8, 9, 10, 11,
Okay.
12. You could go at any time these nights and
That's so.
and see it. But if it says pre-dawn, oh, there it is, November 17th through 18th. So look at this one goes for 3 days.
That's so cool.
So you look at the
75 per hour.
I can't wait. That's
look at the
so
sky and go look in that direction. If you got a compass or you know your
Go
direction,
out that night and watch.
you can go out and look. So this is kind of what it looks like. This is sped up video. See them?
Yeah.
See the streaks coming
Oh,
by?
that is so.
This is
cool.
sped up. Now this, do you notice that they all seem to be coming from a point?
Yeah.
Yeah.
Well, that tells you that's the direction that the Earth is moving. You know, like if you're driving through the rain goes by this way, and it goes by that way, you're moving this way.
There are so many questions.
So this was the first evidence that any philosopher had that the Earth was moving.
I have so many questions right
Ask one of them.
now. Why is it's not the meteors coming this way, but the stars moving that way?
Okay, so the reason why the stars moved, and you missed the first month where we talked about all this, but the reason why the stars move is because the Earth spins. Oops. So the Earth is turning like this, and the stars are way out there, kind of fixed. And so as the Earth turns, it seems that everything moves by in the sky. Does that make sense?
Yeah.
The Earth is turning. This is sped up really fast.
And at the same time, we're moving forward.
At the same time, the Earth is moving through space around the sun. So the Earth moves around the sun. And I actually need to get these models for something we're doing today.
What's that over there? There's a
The things that look like clouds,
yeah.
that's the Milky Way. So, hold on. So the Earth is in a galaxy we call the Milky Way. And the Milky Way is like a flat disk. Here, I'll use her disk here. Will it come up? I better not. Anyway, the Milky Way is like this disk here. We're a star that's in the disk. And so, if you look along the disk, you see a lot of gas and dust and light. That's what that streak is. That's what all that is right there. That's gas in the Milky Way disk.
So we're going this way, along with
What's that?
So we're going like that way alone.
Well, we're on our planet, and the planet's turning. So it's just moving by along with all the stars. So yeah, that's a cool picture, isn't it? So let's take a look at this video here. This shows how it works. Here's a
When
comet.
mounting the sun or a Jovian planet too closely, comets and asteroids can break into small fragments. If the debris intersects Earth's orbit, it can produce either delightful meteor showers, as is often the case with comet fragments, or
Let's get rid of her voice. Okay, let me back this up. Okay, so here's the sun, here's the Earth, and the Earth is orbiting the sun. There's the Earth moving, see? And this is a comet. And it breaks up into pieces. Every time it passes the sun, it gets broken up a little more. But the pieces keep moving. And here's the Earth going around the sun. And here come the pieces. And the Earth can strike the pieces.
Is it twice every year?
Well, it doesn't strike them on the second route. It only hit them on the first route.
And what is that?
So wait, here come the pieces again. The pieces are going to come back around. The Earth's going to hit them again the next year. Come on, pieces. There we go, see? Bam, there we hit one of them. So those pieces are really small. That's a meteor shower. The Earth is hitting a bunch of pieces.
Do the pieces actually make landfall, or?
Most of them are just the size of a grain of sand, and they burn up in the atmosphere.
Okay, gotcha.
So that's what this is. We're going, whoops. The Earth right here is going through a bunch of those pieces, and that's why you see all these shooting stars. That make sense?
And it's just like small, like how much, you know,
Like the pieces that are in space are the size, most of them are the size of a grain of sand,
they still
or even smaller. And they'll still burn up like that in the atmosphere because they're going so fast. They get real hot and they start glowing and give off a lot of light. Most of them don't hit the ground, but some of them could, and if they do, it's a meteorite. You need to see that show, Meteorite Men. Y'all ever seen Meteorite Men?
Never have.
All right, now we're starting the next chapter here, which is
Tidal forces.
tidal forces.
I'm serious.
One thing that's really big in astronomy is the tides.
Okay, set that off.
10 points if you know what this is from.
Howdy, all right. All right, then. Howdy, all right. All right, then.
Anything about it?
Where'd you go?
Never watched it.
Howdy, all right. All right, then.
Purple correct. Orange correct.
Oh my god.
Blue correct.
Okay.
Feeling good.
All I could do is sit there watching.
Green correct.
Wait,
Spelled
Peach
wrong.
is
But
coming.
That's roller, sorry.
anyone else?
Yeah, Peach.
That was awesome.
Let's go, Peach. Let's go, Peach. Thank you. No,
Oh.
Peach is incorrect.
I'm sorry.
It's Shrek.
Shrek.
The gun drum. I'm sorry.
He was getting intimidated.
Howdy, all right. All right, then.
All right. So, you need to understand what tides are. Tides are stretching forces that cause bodies to stretch. The tides on Earth are caused mostly by the moon, but it's also the sun.
Is this the
So-
same chapter we learned in marine bio?
We did study this in marine bio too, but we get a little more involved here.
This is great for me.
So pretend that's the sun, That's the sun, and here's the earth, and here's the moon. So wherever the moon is going around, the moon orbits the earth, right? How long does it take for the moon to go around once? About a month. So they call it a month, a moon. So anyway, here we are, here's the moon, and wherever the moon is, there's a bulge facing the moon. And on Earth, it's a big bulge of water that bulges up some. And remember, the Earth is spinning, right?
Right.
So,
Did we learn this?
we already learned this in marine bio.
It's confusing me.
How is it confusing you? It's the same thing again.
I was like, oh my gosh, Mr. Willis is already all.
I do know this.
No, we just don't even know.
So, if we put ourselves right here on the globe, I have a little pin where St. Simon's is. Let me find St. Simon's. Wait, where? I'm on the wrong side.
Yes.
Here we go. There we go. Okay, there we are right there at that pin. Okay? And let's suppose the moon is right here. So there's a big bulge of water pointing toward the moon, right? So when the Earth spins, now we're under the big bulge of water. That's high tide. When we're right there, we're not under the big bulge of water. That's low tide. There's a big bulge of water, though, you got to understand, on both sides of the Earth. Because the Earth is stretched lengthwise by tidal forces. Let me show you why we have a big bulge of water. I need a girl with long hair. Come here, Maggie.
Weird thing.
I'm going to spin you around.
It's like deja vu.
I know.
Okay, you got to hold hands and hold on tight, okay? And then I'm going to spin you around. What I want y'all to do, put your hair back. Yeah, there you go. I want y'all to watch your hair in the back, okay? Watch your hair. Hair's going to go back. We're going to just spin around. See your hair going back? Okay, that's good enough. That was fun. Give her a big round of applause for dancing with me. Did you see her hair going back?
Yeah.
That's just like the water on the Earth goes back. The moon is pulling this way, but the water goes back that way. So the water goes both forward on this side and back on that side. So, low tide, here's the moon is right here. I'm going to set it down here. We're at low tide in St. Simon's, and then the Earth turns, and now we're under the big bulge of water that's on this side, so we're high tide. And now the Earth is turned so that St. Simon's faces this way. Now we're low tide again. Now the Earth is turned so that St. Simon's is over here under this bulge of water. That's high tide. The bulge of water doesn't come up this high, and it doesn't go onto the land and over us. We're not drowning every high tide. But it just comes up a little higher. The bulge is small compared to the size of the Earth, but it's there.
But isn't there a bulge on every side?
There's a bulge on this side and a bulge on that side. There's not a bulge here and here. You see the diagram there? Does that make sense? So as the Earth turns, you get 2 high tides and 2 low tides a day. So as the Earth turns, you go through high tide, you go through low tide, you go through high tide again. And then low tide again. 2 a day. However, you need to understand this. At the same time that the Earth is spinning and you're going underneath the high tides, the moon moves a little bit. So the moon moves from this position, the next day it'll be in this position, right? So the high tide occurs about 50 minutes later every day because the moon is moved a little bit. And the Earth has to turn a little bit more to reach the bulge again the next day. Yes?
Why are there like higher tides? There's like this bay that I'm blanking on the name up in Canada where like there's like 30-foot tides.
Yeah.
Yeah.
The Bay of Fundy. So when you think about a tide, we have really high tides here compared to a lot of places. And if you look at the coast of Georgia, Florida sticks out like this, and North Carolina goes up like this. So we're in an area that's kind of indented, okay? And so when the tide comes in, the water comes in like this, right? Coming in from the further out. Do you see? Are you with me, Chris?
I am.
So when it hits the coast, it's funneled all towards the middle. And if you're right in the middle like we are, you get a lot higher tides. I like to use the analogy, if you take a squeegee and you squeegee into a corner, all the water piles up in the corner.
Right.
And so if you were in the corner, there'd be a lot of water there. But if you're on the edge over here, there's not as much. So the Bay of Fundy happens to be right there at a big U where everything funnels to it. Yes?
So the tides would be equal everywhere if there was like no landmass?
If there were no landmass, the tides would be equal everywhere. Good question. Okay, so that's the tides, and you need to understand that it's not only the moon that affects the tides, it's also the sun. Now the sun is real far away, but it's huge. So its gravity also affects the tides, but to a lesser extent than the moon. The gravity of the sun is only about half as much as the gravity of the moon on the Earth's tides. So, but there is some effect. So if you have the moon and the sun all lined up together, like we get every time there's a full moon and a new moon, you'll get a lot higher tides than you would if they were at 90-degree angles to one another. Sun, Earth, moon, the high tides aren't as high as when they're all in line like this. When they're all in line, you get higher high tides. We call the highest high tides, we call them spring tides. And the lower high tides, we call neap tides. So this is a monthly tidal cycle. Tides will be real high there, and then not as high here, and real high here, and then not as high here if the sun were there.
All in 1 month?
In 1 month. So you go through these spring tides, which are real high tides, and neap tides, which are not as high tides. When we have spring tides here, that's when you see the water almost up over onto the causeway. Have you ever seen that on like covering the bike path? That happens about twice a month, during new moon and during full moon, when the sun and the earth and the moon are all lined up. Yeah.
I work in Jekyll Island, that's 231. Like over there, like every time like the shifts change from like 3:30. Like it'll be high tide, it'll be low tide then, like the high tide come like around 4:30 and then they go back down, and then like, later on that night it'll come back up. It'll like rise again. I don't know, it'll be weird.
Yeah, well,
it's around the same time every day.
It's not the same time every day. It's an hour later each day.
Well, yeah,
if you check it, right? Or it's 50 minutes later each day, and that's because the moon is moving, and the Earth has to spin a little bit extra to get to that new moon's position. And so compared to the sun, it's about 50 minutes later each day. Check it next time, time it, and see when it's the highest. If you get, that could be kind of a boring thing to do, but anyway, you can do it. This is a good thing showing how this works. This shows the Earth is spinning like crazy, and this shows what the tides look like. So the blue is the tidal bulge. And there you see it, and the sun is over here on the side, on the right side. And so now they're all in line, and you get the big tidal bulge. And now they're 90 degrees, and it's a lot more even around everywhere. And now it's full moon, and you get a bigger tidal bulge. You see what I'm saying?
I do.
Yeah.
Isn't that cool? That's a nice little... And you can see the moon is always half lit. So there's a quarter moon. Now it's waxing, now it's full, now it's waning, now it's a quarter moon, now it's a waning crescent, and now it's a new moon. It shows you everything. Isn't that good? Now, we get to something called tidal breaking. This is something you didn't do in marine bio. Because of the Earth, because of the moon, and the gravity from the moon, because of these tidal forces, the Earth is slowing down how fast it's spinning. When the Earth was formed, it spun around once every 4 hours. Now it only goes around once every 24 hours. And it gets about a second less each year. Every 2 years is about a second. The spin of the Earth is about a second. Takes about a second longer. Every couple of years.
Did you say it used to be 4 hours?
It was 4 hours about 4 billion years ago. It took 4 hours to go around once.
No.
Yeah, huh?
Just because it spins faster?
It was spinning a lot faster then than it is now. It's slowing down. Why is it slowing down? It's because of tidal forces.
So you mean the day was only like 2 hours long?
It's 4 hours long.
Okay.
Yeah, a day is 2 hours and a night is
Well,
2
they would
hours.
sleep. Oh, gosh.
Wait,
This was
yeah.
4 billion years ago. There were no humans.
Well, no, I'm saying the animals, but I guess they didn't have to sleep.
There weren't even animals then. Just bacteria.
Okay.
And they didn't really care.
That's kind of crazy.
So, it has changed over those billions of years, and it's still slowing down. And the reason why it's slowing down is called tidal braking. And to understand tidal braking, you have to understand that as the Earth spins, it twists the tidal bulges. So here's the moon. There's a tidal bulge toward the moon and away from the moon. But because the Earth is spinning, the bulge is twisted. So it's not actually pointed at the moon. It's actually pointed a little in front of the moon. The Earth's spinning turns the tidal bulge a little bit. Let me get this perfectly lined up. So, the way I had just explained it to you, there should be a tidal bulge pointed toward and away from the moon, right? Y'all understand this so far? But if the Earth is spinning, it twists the tidal bulge a little bit. So the bulge is actually pointed a little bit offset to the moon. The bulge is pointed like that way. Just like they show in this picture. And what happens, the moon is pulling on the bulge, pulling it backwards. The gravity of the moon pulls on the bulge a little bit, pulls it this way. And there's friction. The Earth is trying to turn that way, but the moon is pulling on the tidal bulge kind of backwards. And it slows down the Earth's spin.
Well, why is it decreasing? Like, why does it not stay the same? Why is it getting longer and longer?
Because if you're slowing down the Earth's spin, it doesn't take 24 hours to get around. It takes 24 hours and 1 second to get around. You see what I'm saying? You're slowing down the spin of the Earth. It's like the Earth is spinning this way, and the moon is dragging on that spin this way. You see what I'm saying? Did that answer the question?
I don't know.
So right now, Charlie, it takes 24 hours to go around once. But the gravity of the moon is slowing that spin down. So in 2 years, it's going to take 24 hours and 1 second to go around once. And in 4 years, it's going to take 24 hours and 2 seconds. And in 6 years, it's going to take 24 hours and 3 seconds to go around once. You see what I'm saying?
Yes.
So it's slowing down. The gravity of the moon pulling on this offset tidal bulge is slowing down the spin of the Earth.
So in another like million years, are we going to have like a lot?
It might be a
longer day?
24 and a half hour day in a million years, 2 million years. Scientists have taken care of this, though. Scientists add a leap second once every 2 years. You know how we have a leap year? You add a day every 4 years. We add a second every 2 years. They don't tell you about it. They just do it, and all the clocks are adjusted by that second. There's a leap second added every couple of years to keep the day the right way.
I was about to say, because in like a really long time, how are people going to like sleep at the right time?
Yeah, it'll get messed up if you don't add in those leap seconds.
Yeah.
So we add them in. So we call that tidal braking. Now you have to understand something called tidal locking. Did anyone have any questions about tidal braking? You understand the Earth is slowing down its speed of rotation. Yeah.
Never mind.
Are you sure?
And that was because
That's what I'm going to get to. So the moon. What about the moon? Does the gravity of the Earth affect the moon? It does. The moon was once spinning really fast, just like the Earth spins. But the Earth has a lot of gravity, and the moon also has tidal bulges. Now the moon doesn't have water, so it doesn't have water tides. But the entire moon is a little bit oblong because of the Earth's gravity. The Earth has stretched the moon into like an egg. Now it's not enough of an egg for you to visibly tell that it's not round, but it can be measured. It's there. There's more rock facing toward the Earth than there is on the edges. You see what I'm saying? It's a little bit bulged, like I've made it with my hands here. Now, a long time ago, billions of years ago, the moon was spinning really fast. But and the bulge was pulled on by the Earth's gravity, and that eventually slowed down the spin of the moon, and now the moon has stopped spinning so that the bulges always face the Earth. But it hasn't completely stopped spinning, because as the moon goes around the Earth, the bulge turns the moon, so the bulge always faces the Earth. So we see the same face of the moon at all times. That's where the bulge is. And the other side of the moon, we call that the dark side of the moon. Have you ever heard of the dark side of the moon? Yeah, like the Transformers movie. And before that, it was a Rolling Stones album or somebody. Somebody had an album.
I think it's Rolling Stones.
Some rock band. Wasn't Rolling Stones. Pink Floyd.
Yeah.
So Pink Floyd had an album, Dark Side of the Moon. What they're talking about is the side of the moon we can't see. Because the moon keeps the same face towards us at all time, because the gravity of the Earth has stopped the spinning of the moon. Eventually, the gravity of the moon will stop the spinning of the Earth, and the Earth will have its same face toward the moon at all times. But that's going to be billions of years into the future, because the Earth's so much bigger than the moon. Yes?
Wait, so it's going to be night on one side of the Earth?
No, because night depends on the sun.
Oh, right.
Remember? Well, oh yeah, I see what you're saying. Yeah, the Earth will spin around once each time the moon goes around once, when the moon stops the Earth from rotating completely. So if the sun was over there on St. Simon's, I'll put the clip for there's St. Simon's. So if the same face of the Earth always faced the moon, then it would be day at this part of the month, and now we're turning, now it would be night for a couple of weeks. Until
oh my gosh, that'd be
it
so
came back, it'd be a different world, wouldn't it?
If it was night.
But you don't have to worry about that. The moon is not going to slow down the Earth's spin that much for billions of years into the future. And by that time, the sun will have expanded and swallowed up the Earth.
Now we get to it. It's alright.
So that takes care of the problem. We don't have to worry about... They call this tidal locking. When the same face points towards a nearby body, it's called tidally locked. And the moon, as you can see on the left, is tidally locked to the Earth. The moon does not... This thing on the right is showing you what would happen if the moon didn't spin at all. This is actually not what's happening. I wish I could remove that. They're just comparing what would happen if the moon didn't spin at all. The moon is still spinning, but the moon rotates once a month, so it keeps the same side always facing the Earth. If you notice, the same side of that moon always faces the Earth.
Have we seen the dark side?
Yeah, we've seen the dark side of the moon because we've flown a spaceship. The Apollo spacecraft went around it and took pictures of it.
What did it look like?
It looked different from this side. Okay, we thought it would be all the same everywhere, but this side has a lot more dark material. And this side has light material. And higher, the elevation is higher on this side than this side. It's weird. We're going to talk about why the moon has differences on its side. But it has to do with the gravity of the Earth pulling the rock and pulling the center of the moon a little off center. And it makes the crust on this side thicker than it does this side. So it looks a little bit different. We'll talk about that later when we talk about the moon.
So it's just like tidal locking is just like.
Tidal locking. Here's a definition of
Like
tidal locking.
when
the gravity of a body stops the rotation of the gravity of another body to the point at which the same face points toward that body, the original body. The same. The moon keeps the same face towards the Earth.
Wait, I got the gravity of the body stops.
When the gravity of one body stops, we can say when the gravity of body 1 slows the orbit of body 2 to the point that the one face of body 2 is always facing body 1. It might be easier if you think about it in terms of the Earth and the moon. The moon is tidally locked to the Earth because the same face of the moon always points to the Earth.
So basically,
It's an easier way to say it.
You're talking about how the orbit matches like the rotation.
That's a super way to say it. The orbital period is
Matches
equal
the
to the
rotational
rotational period. That's the best scientific way to say it. And you came up with that, Aubrey. Do you know how good that makes you? That makes you like a scientist.
No.
When the orbital period matches the rotational period, the two bodies are tidally
Because like
locked.
when you're saying body and body, like it was
That's too much. Yeah, it's too confusing. Yeah. I agree. Your way to say it was better. But you have to understand what orbital period and rotational period mean to understand your way you're saying it. That's if you looked it up on Wikipedia, I bet it would say that. The rotational body matches the rotational. How'd you say it? The rotational orbit matches. The rotational period matches the orbital period.
The name given to the situation when an object's orbital period matches its rotational period.
Bam.
Wow. 28 days to go around the Earth, 28 days to rotate once around its axis.
Bam.
Dang, Aubrey.
You're doing
10
it.
points for my team.
Yeah, that's 10 points for our
You're
team.
doing it. We're about out of
She's my
time.
third pro.
I had some video footage.
So we should get him one.
What do you say?
I think Chris was about to say that.
Okay, do me a favor. Read this video is in your book. Read your textbook tonight and make sure you watch those videos.